The other type of symmetry that we like to look at in this class is for complex signals, and that's called conjugate symmetry. And as the name implies, it will involve taking the complex conjugate of the signal. The learning objectives then are to basically understand its definition and be able to apply it to complex signals. So we still have for complex signals even and oddness. We can define even signals to be ones where x of t is equal to x of minus t, and odd signals are ones where x of t is equal to minus x of minus t. And we can define the even and odd parts, but there's this more important notion of symmetry called conjugate symmetry. So a signal is conjugate symmetric if x of minus t is equal to the conjugate x star of t. And similarly for discrete time, x of minus n is equal to x star of n. And there's also a related definition of conjugate antisymmetric, which is kind of like the odd type version of this, where x of minus t is x star of minus t and x of minus n is x star of minus n. But usually we talk about conjugate symmetry a bit more often, although conjugate antisymmetry does appear when we talk about Fourier transforms. So suppose x of t is conjugate symmetric. And since x of t is a complex signal, it's a little bit hard to think about graphically. So we have two different decompositions, both to Cartesian representation, and we also have the magnitude phase representation. So we can see, well, if the signal is conjugate symmetric, what does that mean about its decomposition into Cartesian or magnitude phase? So we have x of t. X of t is the real part plus its j times its imaginary part, and x of minus t is the real part plus j times the imaginary part of x of minus t. And what is x star of t? Well, it's the real part of x of t minus j times the imaginary part of x of t. So now what we're doing is we're saying that these two things are equal to each other. And so that means that the real parts have to be equal to each other and the imaginary parts have to be equal to each other. So that's saying that the real part of x of t is the real part of x of minus t, and that is that the real part is even. Real part is even. And then the imaginary part says that, imaginary part of x of t is minus the imaginary part of x of minus t, so that means that the imaginary part is odd. So that's actually much easier to think about than this sort of x minus t is x star of t. We can say if it's conjugate symmetric, the real part's even and the imaginary part is odd. Okay, so let's suppose that x of n is conjugate symmetric. It's a complex signal, so okay, what about the magnitude phase representation? You can look at this, for example, for a discrete time signal. So x of n is a discrete time signal. It's conjugate symmetric. It's complex valued. So let's see what happens to the magnitude and phase. Well, again, we can write x of n as in terms of its magnitude and phase. We can write x of minus n in terms of its magnitude and phase. And for x star of n, remember the magnitude stays the same, but the phase switches the sign. The j switches the sign in the phase in the exponent here, right? So we get this minus j phase of x of n. But again, we're saying that these two things are equal to each other. So that is to say x of minus n is equal to x star of n. And so that means their magnitudes have to be equal and their phases have to be equal, which means that x of n has to equal, the magnitude of x of n has to equal the magnitude of x of minus n. So this is even. And the phase of x of n here has to equal minus the phase of x of minus n. So this means that it's odd. So if you have a conjugate symmetric signal, the magnitude is even and the phase is odd. So in both our representations, Cartesian and magnitude phase, we can see that the conjugate symmetry implies our original, earlier type of symmetry for the different parts of the decomposition. Okay, so let's look at an example. Suppose we have a signal. Now I'm going to call it x of omega. I'm going to do that because when we see it, it's going to be a function of omega. But so it's equal to 1 over j omega plus pi of delta of omega, a Dirac delta function at 0. Well, so we can check the definition. We can just plug in x of minus omega. So we get minus 1 over j omega plus delta of pi times delta of omega. because the delta is at 0, so when I take minus omega, it just stays at 0. And this is just equal to x star of omega, because we can see that the imaginary part has switched signs. So this is in fact x of minus omega is x star of omega, and so this means that this signal in fact is conjugate symmetric. And later on we'll see that this signal is actually what's called the Fourier transform of the unit step function. So here's a little exercises for you to try at home. So check if the following signals are conjugate symmetric, just applying the definition. And you should be able to get some insight into how the definition works. You can look at these in terms of magnitude and phase, or you can look at them in terms of the Cartesian representation, and you'll get a better feel for how conjugate symmetry works. So that's all that we have to say about symmetry. And so now we can move on to new and more exciting topics.